In section 5.4, we're still working with binomial probability problems, only in this section we're finding the mean, variance, and standard deviation of the distributions. Lucky for us, these equations are nice and simple. To find the mean, it's just n times p, sample size, times the probability of success. Variance, npq, and standard deviation is always just the square root of the variance, so radical npq. And that's really all we need to know for this section. So let's apply it to Gregor Mendel's famous P experiment, where he speculated that there was a 0.75 probability that an offspring P has a green pod. That's going to be our probability of success. He generated a group of 580 offspring Ps. That's our sample size. So our important information is here. We want to find the expected number of Ps in this group with green pods, the standard deviation, the maximum and minimum usual number of Ps with green pods in a group of 580. And then we want to look at his actual results. So he had gotten 428 Ps with green pods. Is that unusual compared to what his initial assumptions were? As a side note, we did a problem just like this back in section 5.2 when we were focusing on probability tables, probability distributions. We were dealing with a much smaller sample size back then, just 5 Ps, and we had a table with 0 through 5 at the top and the corresponding probabilities underneath it. And the way we found the mean was with this equation up here, sum of x times p of x, and standard deviation was with this one right here. Now that we know this is binomial and we know the binomial equations, we can find the mean with just n times p. That's the expected number or the expected value. Standard deviation is radical npq, and we get 10.428. So in a group of 580 offspring Ps, we would expect 435 to be green and there to be a standard deviation of 10.43 green Ps. Based on that, let's find the minimum and maximum usual number of Ps. Remember, anything outside of 2 standard deviations from the mean is unusual. So we subtract 2 standard deviations from the mean to get the minimum usual value, add 2 standard deviations to get the maximum usual value. Those are our minimum and maximum usual values. How does this compare with what Mendel actually observed, which was 428 Ps? That wouldn't be unusual at all. That's right in the middle there. Okay, so that's within 2 standard deviations of the mean, so it does not provide evidence that the 75% estimate is incorrect. Example 2, we flip a fair coin 20 times. When we talk about a coin being fair, we mean that there's a 50% chance of it being either heads or tails. So our important information is here. Find the mean, n times p. We would expect there to be 10 heads. There would be an average of 10 heads. Find the variance. Variance is just npq. Variance is 5. Standard deviation is just the square root of the variance. Square root of 5 is 2.236. Would we be surprised if we flipped a coin 20 times and it resulted in 15 heads? Explain. Well, we want to use the minimum and maximum usual values. So in other words, is 15 more than 2 standard deviations from the mean? So our maximum usual value would be 14.472. 15 is above that. It's beyond 2 standard deviations from the mean. So it would be surprising to get 15 heads if we flipped a coin 20 times. One last example that kind of covers the wording on how these problems are presented to you. Based on a 74% national retention rate, does a college where 522 of their 603 freshmen returning the next year as sophomores have a right to brag that it is an unusually high retention rate? Explain. All right, so if that 74% national retention rate is true, and we have a group of 603 freshmen, how many would we expect to return? Okay, we would expect, or we would have a mean of 446 returning. Okay, now is this unusual? So to figure that out, we need the standard deviation. Standard deviation is 10.77, which makes the maximum usual value 467. Okay, this is much higher up here than the maximum usual value. So yes, 522 freshmen returning out of a class of 603 is unusually high.